goes through more than just say than supervised learning, goes through unsupervised learning as well, but the data set are not related to science of science. Now, the good thing is that the book and the or the website of scikit-learn has this great visualization of, how you can decide what to apply, and kind of start from here. You see how big your data is. Yeah, it's awesome. I didn't do it, so thank you to whoever made this. And depending on the number of samples, depending on the kind of problem you have, then it tells you what method to use. So, and this goes through the iris data set, which is this data set of, it's a classification problem, and you're trying to classify flowers into 3 categories based on different measures of the kind of the structure of the flower itself, the physical structure. And then it goes through more details about how the API of scikit-learn works. And I wanted to show you an example of unsupervised learning. So, in the iris data set, see, you have, well, I didn't run it, so let's see here. So in the iris data set, you have 4 features. So imagine that you want to plot these flowers. It's impossible to plot 4 features, 4 dimensions, right? So you can use something like, one technique that you can use is something called principal component analysis to plot the features. And that's what this example does. So it does a PCA, it gets 2 components, and with that, let's see what happens. Oh, I have to rerun this. Okay, so I have to run it from the beginning. Okay, so I run the PCA, and then you can see that now these principal components, you have to read a little bit about what it means, but they might be a little hard to interpret, but at least you get a sense of that there is a way of splitting this 4-dimensional, there is a way of mapping this 4-dimensional space that is this, all these measures, these 4 dimensions, there is a way of mapping them into 2 dimensions, and this is what this is showing. You can also do clustering of them based on these 2 PCA. And here it goes to a more complicated example when we're doing digit classification. So there's this famous example of digits where you have the image of a hand-drawn digit, and then you want to classify it into 8 and to 10 digits, well, from 0 to 9. So how to do that image classification. It's very fun. Actually, it does dimensionality reduction. So now what's interesting about this is if you think about it, these images are 8 by 8. So you have 64 dimensions, or 64 dimensions. So this, with this technique that we are applying here with scikit-learn, we can map these 84 dimensions into whatever many dimensions we need. So here we're going to map it into 2 dimensions so that we can display it. And so we now map these 8 digits into 2 dimensions, and you can see that there is some clustering. So these are all the zeros, these are all the ones are over here, and you see that there might be some relationships. So these are the zeros. I believe these are the what color is this? These are the 6. So, and it makes sense. Like 6 is similar to 0. It's like a little, it's like 2 bubbles, and 9 should be also nearby, but it's not. So I guess my explanation is failing. 9 is over here, so I would expect it to be closer to 6, but it's not. So, but at least you can project them. They're like separated from each other reasonably well. And here below, they do classification on digits. So they get 83% accuracy. And then you can compute, you can do confusion matrices to see the kinds of errors. And the kinds of errors that it's making make sense. Choose. Sometimes I very often confuse with eights, so on and so forth. So depending on the kind of problem that you will do for the summer school or in the future, you might want to use this tutorial. But again, this is borrowed from the book. Now for our little article, so I'm just gonna, this is a shameless plug. So I'm ashamed, but not really. We took the authors and we mapped them into 2 dimensions as well. So this is we took like the abstracts of the papers. So this is like NLP plus unsupervised learning. We took the abstract of the paper and we then mapped them using UMAP, which is an unsupervised way of mapping this very high dimensional, I think it was 128 dimensional vector into 2 dimensions. And you see that there is some clustering, like neuroscience around here. These are all people, all these dots are people. So neuroscientists are here, and they're very close to, what is this, education, literature, and then you have chemistry here. So presumably chemistry and neuroscience are kind of far away, and then you have these islands. And what are these islands? Physics, okay? These islands of knowledge, physics, but then they sometimes interface with evolution, no, what is it? With chemistry and engineering, and that makes sense. Okay, so you can get, I mean, this is unsupervised learning, and you might get, some interpretability out of this. But this is a similar idea to what you saw in the tutorial. Any questions about this? I know that is a lot. I know that this is hard to capture what's happening, but the most important message to me that you can get out of this is, okay, there are different model complexities. They buy you different trade-offs between how interpretable and accurate they are, and you should show you a proper way of comparing different models and picking the best one for your data while avoiding overfitting. This looks fascinating. Just a quick question. So expected vectors are a way of computing. It's like an NLP technique, and I'm going to cheat here. So you take a string, you take an abstract, and it computes a representation, but it's more specialized in the sense that they learn this mapping from not just the papers themselves, but the citations of the papers. But basically, you give this an abstract of a scientific paper, and it gives you back a vector. And you can use that for recommendation for any kind of task. Any other question? Okay, so I wanted to, something that kind of escaped my mind while we were discussing in the previous section. Oh, what is the citation of this for this article? It just came out, so I don't know what the proper. Let's see. Cite this article. So this is a proper citation. Is that what you mean, Mary? Yeah, so that's the proper citation. So one thing that escaped my discussion was when you're trying to interpret things, one of the big risks when you're doing AI is biases, but other kinds of biases. And this is very, very, very important. And we'll discuss this in more detail next Monday with mentors that actually have studies extensively. So we have Aaron, we have Dan, Larimore, and we have an amazing panel, and they all study these factors that get into the data that you're using. So you can have gender factors, demographic and race and demographic factors that might get in the way of your prediction. So be careful. Let's say when we're predicting citations and we are using things that represent, let's say, certain countries, or you might get biases that kind of through the cracks, and you might say, oh, my method is amazing, it's having this amazing prediction, but actually what it's doing is actually, in a sense, perpetuating these biases, is maybe trying to take hints about maybe the language difficulties of the authors or certain regions of the world. So you have to be very, very, very careful about that. So every time you do an interpretation, you have to use your criteria to say, well, using the zip code, let's say in the US, zip code is like the geographic area and unfortunately, for many reasons, the US is very segregated. So sometimes using the zip code is a proxy for race. And if you're doing any prediction that involves zip code, you're basically giving a lot of information about race, and that could produce all kinds of nasty results in your predictions. So always be mindful about that. And I want to advertise the panel, but I also want to advertise the talk by Roberta next week. And I haven't heard this talk, but I just read the abstract. I'm really looking forward to hearing about this. So next Tuesday, she's trying to quantify these things. So a lot of the things that we do in Science of Science are based on data sets about science, of how science was done 20 years ago or 30 years ago. And as we all know, science back in the day maybe was more male dominated, by very Western focus. So if we're trying to infer anything about how science should be done, we should be careful that, well, that's the data that we have, but that doesn't necessarily mean that that's how we should do science today. Okay, and Roberta, I hope, discusses those issues next week. And with that, I'll say thank you so much again for staying with me and joining the second week. Please continue the conversation in Slack, and any question that you will have, just through Slack is the best channel. So I'm gonna close this Zoom to save the video, and I'm gonna post-process it and post it on GitHub, not GitHub, on YouTube. But then we're gonna reopen the Zoom so that you can discuss with your peers. Okay. So, and with that, then see you tomorrow. We have a very exciting session on network science with Stephen, not David. Right. Bye.